Hi all, welcome to Geeks for Geeks. I am Utkarsh Kesarwani, your DSM mentor, and going to solve today's problem of the day. So the name of the problem is closest neighbor in BST. Given the root of a binary search tree and a number k, find the greatest number in the binary search tree that is less than or equal to k. So let's start solving. So in the question, they give you a root node, root node of a BST. So they have been given you a BST. So properties of a BSTs are, if we find the in order of a BST, so they are sorted, and the left subtree value, the left subtree node values are less than the root node value, and the right subtree's node value are greater than the node value. Correct? And they also give you an integer k, and you need to find the greatest number in the binary search that is less than or equal to k. Means you have to find let's suppose x which is greater than or equal to this k, and this should be greatest, okay, greatest possible. So we have to find out this. Okay, so how we can do this? If I will talk about the brute force approach, so what you can do, since you know that the in order traversal is always sorted, so you will find out the in order traversal of this binary search tree. Let's take this example, and if I will write the in order traversal, so in case of in order, how we move: first left, then node, and then right. So first we will go to this left, so 7 to, yeah, from 2, then 7, then 8, then 10, then 5, then 10, and after this 10 we will move to right, and then left first. So 11, then 15, and then 16. So you can easily find out this. Okay, now they give you k is equal to 14. So we need to find out the number which is just less than or equal to this. So what we can do, we can traverse from the back. Is this less than or equal to 14? No. Is this less than or equal to 14? No. Is this less than or equal to 14? Yes. So this is our answer. Correct? So if we will talk about the time complexity of this solution, since you are finding out the in order traversal, so for that you need to visit each and every node in this tree. So the time complexity is O of n in that case. Okay. Let's talk about the optimized solution for this. Optimized solution. And also if I will talk about the space complexity, since you are storing it in some vector or somewhere else, so this space complexity is also O of n. Let's draw this example: 10, 7, 15, 2, 8, 2, 8, 11 and 16. 11 and 16, and k was 14. I will tell you all the cases here. Okay, so let's take first k is equal to 14. So what we can do, uh, they will give you the root node. So when I will come to this 10, I know that this 10 is less than or equal to this 14. This 10 is less than this 14. So and also we need to our question was that we need to find a node value that is less than or equal to this 14. So it may be possible since this is less, this 10 can be the answer. So what I will do, I will store 10 as my answer, and I will see further whether any number exists greater than this 10 and less than or equal to this 14. Okay, so now since k was greater than this 10, so if we will go to the left side of this 10, so since it is a BST, so all the values will be less, but we want more value, greater value from this 10. So we will move to the right side. Now we will come to this 15. Since this 15 is greater than 14, so this 15 cannot be our answer. So what I need to do now? Now I want a less value. So for less value, we know to get the less value from the current value, we go to the left. So we will move towards left. Here it is 11, and this 11 is greater than from previous answer and also less than this key. So we will update our answer. Now we will again see, since this 11 is less than 14 and we wanted an answer that is more closer to this 14, so we want that can we get an answer which is greater than 11 too. So for that we will move to the right side, but since there is null, so we will backtrack. Okay, so in this case our answer is 11. You can also see here the answer is 11. Okay, let's suppose now for this k, our answer was 11. Now let's suppose uh, our k value was 7. Okay, so we will also, what if suppose the condition fails, means since we need to find a node that is less than or equal to that k value, but if all the nodes are greater than, so in that case our answer will be -1. Okay, so always initialize your answer with -1. Now we need to find for this k is equal to 7. We will come to this 10. Is this 10 less than k? No, it means this 10 cannot be our answer. We need a value which is less than this. So we have to go in the nodes which are less than this 10. So definitely we have to move to the left. Whenever I reach to this 7, I got to know that this 7 is equal to this 7, the value of k. So whenever the value is equal, it means that is the answer. We don't need to find because that is the perfect answer. So update your answer as 7. Let's take one more example. My k value is 1. So in the starting, answer will be initialized as -1. Now we came to here. This 10 is greater than k, so we have to go to the lower values. We move to the left. 7 is still lower values. 2, it is greater than 1, is still left. We now get null. So it means we are not able to find any values. We will backtrack, and our answer will be minus of 1. Correct? So what you can do, you will start from the root node, and then you will see if this value can be your answer. If this value can be your answer, so you will store it in the answer. Okay, you will store this value in your answer, and then move to left or right according to condition. So let me write the condition, uh, or let me write the pseudo code. So what you will do, void solve, you have node here, so node is star root, then you have a answer variable, so I'm taking it by reference. Okay, and you have k, int and k. So what you will do, if your root is equal to null, so in that case you have to just backtrack. So return. Now what you will do, you will check. What you will check, if your root of data, if your node value is less than or equal to, uh, if your root data is less than k, so what it means, this can be a perfect answer. Correct? If your root of data is less than k, so it may be a perfect answer for you. So what you will do, you will update your answer. Update your answer. So you will update your answer. So how will you update your answer? Your answer will be equal to, root of data. Correct? And now you will further call. So solve. And now since your value was less than this k, so you want a value which is more closer to k, so you will move to the right side. So root of data, root of uh, right, comma answer, and comma k. Okay. Else if, let's suppose your root of data is greater than k. Okay, so what you will do in this case, since your this value is greater than k, it means your answer will not update here because this value is greater than k. So your answer will be equal to, answer will not update, but you have to search in the left side because you want a lower value. So root of left answer, comma k. Else if the value is equal to k, so your answer is uh, root of data and just return. Okay, so let's do it. uh, we will write a function. So void solve, yeah, void solve node star root int and answer and int k. Okay, if your root is equal to null, just return. Else what you will do, yeah, now if you, you will check if your root data is less than k, it means this can be an answer. So if this can be your answer is equal to root data. And now you will check in the right. So root of right answer k. Else if your root of data is greater than k, so if the value is greater than k, so that can't be your answer. So the answer is, you will not update your answer here and you will just call for the left side. So root of left and answer comma k, and in the last it means the root of data is equal to k. So in this case you got the perfect answer and don't need to check for other values. So just update your answer is root of data and just return. And here create a answer variable initialize with -1 and call this function. So solve root answer and k, and just written answer here. Take this also by reference. Yes, so we forget to add the return statement here. uh, if we will go in this case, and after going to this case we also have to return, no? So return. Okay. Yeah, let's submit the solution. Yeah, it's submitted. So if I will talk about the time complexity of this solution now, so you can see that we moved like this, means in each step we are moving one step down uh, in the height of the tree. So the time complexity will be O of h. And if I will talk about the space complexity, so since we are only using the recursion space, that is also equal to O of h. So thanks for watching the video. If you have any doubts, you can comment below, and have a good day. Bye. Take care.